Hello, everyone. First, I want to thank you for organizers for inviting me here for this inspiring workshop. I'm very looking forward to the interesting discussion we'll have. And today I want to talk to you about something. I make up the name as like topological defects to boundary, and I need to say that I'm a condensed matter theorist. So this talk will be way less mathematical than all other talks. But still, the problem we want to um, talk about and the objects we will study is very similar to that has been studied in high energy, in, say, TQFTs and mathematical physics using higher capabilities. And here's our attempt as a condensed matter theory, how are we approaching this kind of new topics. Um, so first, I'd like to thank my collaborators. That's David Stephen, the postdoc in University of Colorado Boulder, and my postdoc advisor Xie Chen from Caltech. And this talk will be about two works that are going to appear soon and hopefully maybe next week. So mainly the talk will be trying to it's actually two applications about so-called symmetry topological order or symmetry TFT, combining it with defects and see what interesting physical consequences we get using these tools. And the first one I'm talking about is more conceptual. It's the ending conclusion is that we want to argue that the whole collection of defects of any dimensions, one dimension, two dimension or higher, we collectively define it as low entanglement excitations, and using the tool of symmetry border and invertible defects, we found that these kind of excitations in non-trivial invertible phases actually have always one-to-one correspondence with those in a trivial product states. And thus, results will work for all the familiar invertible phases, such as SPT phases, Rana chains, or P plus IP superconductors. And then we want to go more concretely, so the first result is a bit conceptual. So we want to say what more precise things we can say within this defects, and then we'll focus on something called this Marana chain defects, which is appearing in 3+1D fermionic toric code models. It's a particular Z2 gauge theory with emergent fermions. And when we will talk about when we bring this kind of line topological defects from the bulk to boundary, it infers some interesting new results on the boundary. First, we can derive in our condensed matter way that we confirm that there's a distinct type of gapped boundary. And then we can consider the transition from this new type of boundary to some more traditional gap boundary. And we confirm a physical picture that these two gap boundaries are loop condensates. And this loop energy has a unique signature at the transition. The energy will the energy cost will be 1/L. So those are some dynamical detail we will talk about in the second part. So for that, let me begin the first part. So first, I want to introduce our objects. Because we are always seeing that there's higher dimensional excitations or defects that have been very everywhere and driving more attention in recent years. Then the most familiar ones is its domain wall defects. For example, in 2D, it could be a line defect. And the second that always appear is that in some deconfined phase of G gauge series, we have to consider some excitations called flux loops. It's a necessary object to consider because the defining feature of this series that this loop winds non-trivially, has a non-trivial braiding with a point particle. But these defects we usually talk about is like line defect, surface defect. We talk about them in a different way than the point defect, point excitations we talk about. For example, how we generate it. In condensed matter, we actually don't generate it by some local operators. One way to generate it is we modify the Hamiltonian. And another way to generate it by applying some unitary operators, which is usually some non-local operators on the ground state. And these objects, since we study them, but actually they're not energy eigenstate because we don't need them to be. They're good enough if it can roughly maintain its form for a finite amount of time. It's a legitimate topological defects. And then the last important feature is that these defects, they actually have always entanglement area law, because they're always the ground state of some modified Hamiltonian with a gap. So this low entanglement feature is also preserved. So then these kind of defects, these kind of like excitations, we found that some like static defects we always study, they also share these properties. The one more interesting example is this in 2+1D toric code, you can have this line defect, so-called ion exchange defect. The anions, when passing through this line, the E anion becomes M anion. So now it motivates us to have some more unified operational definition for to consider excitations and defects in a unified way, and especially we want to keep track of those excitations that has low entanglement. And then we can borrow some intuition from quantum information, and we found that we can use quantum circuits to define such kind of low entanglement excitations. So it's defined in this way. So in the ground state of a gapped Hamiltonian in D dimension, we want to consider a K-dimensional excitations. And first of all, you need to be a gapped ground state of a Hamiltonian modified only along the excitations. That's how you define the dimension of these excitations. And then we ask what's the equivalent conditions. And that's is motivated by definition about gapped phases in condensed matter. So nowadays we define gapped phases in a K dimension. They are equivalent phase if they can be related by a finite depth quantum circuit. For example, those SPD phases, they are short-range entangled phases. You can always find a finite depth local unitary to disentangle this phase to map it to a trivial product state. That means that these two phases, if there's no long-range topological order, they are actually equivalent. If there's no like extra symmetry to protect them, they're equivalent. So that motivates us to define this equivalent condition. So if two defects, they can be related by a K-dimensional finite depth quantum circuit, they are equivalent. And if we impose symmetry, they need to be symmetric of a finite depth quantum circuit. And with this, we know that trivial types should be defined as creating from the bulk ground state by a K-dimensional finite depth quantum circuit. And then we're left with non-trivial ones. So non-trivial ones must be like beyond those trivial ones. Then there's two ways to go beyond that. One is that they can create it by a K+1 dimensional circuit. So a K-dimensional excitations, if it's non-trivial, it can be created by a K+1 dimensional circuit. For example, that's how we created the domain wall using circuit. And the second is like we can also use them to like it's still a K-dimensional circuit, but it's no longer finite depth. It can be linear depth. And indeed, so we found that this kind of linear depth sequential circuits is always works. Sequential. Does this work? Okay. So sequential circuit means that at each time step, you only apply a local gate somewhere, and you do this in a sequential way. And since at each step, you only like apply a local operator, so the entanglement can grow at most this much. So whenever you have an entanglement cut, it only like cuts through a finite number of gates. That's why they always preserve the entanglement area law. Well, starting from whatever state ground state you start with. So these are two types of circuits. They can give non-trivial excitations, but still keep the entanglement low.
Can you generate this equivalence relation if instead of finite depth circuits, you just use paths in Hamiltonian space that do not close the gap?
Yes, we think there's a correspondence to that, and many of the circuit is it's like found out using that intuition. Yeah, it's not, it's empirically right, but cannot like.
Maybe more basic question. So these quantum circuits, they're unitary operators, right?
Right.
Okay, so that's like a particular type of unitary operator where you don't operate on all the state space, but sort of on bits and like the
Right.
So they're a specific type of unitary. So
Yes. So for example, using this definition, we found like domain wall, it's a 1D non-trivial excitations in a symmetry breaking state. And then this flux loop is also a non-trivial 1D excitation since it can always be created by a 2D finite depth local unitary. And then this lines defects that exchange anion that I talked about, you can create it in two ways. One, you can use this 1D linear depth sequential circuit. Something look like this. You apply it in a sequential way along this line. Then you create this line defect that exchange anions. And then it can also be created by a 2D finite depth circuit. Sometimes it's also called pump unitary operators because you apply this finite 2D circuit around this region and it pumps a line defect to the boundary a bit. And then when anion moving through this string, E string, when it goes through, it becomes an M string. And then you can ask like, okay, I have a good operational definition now. Then let's say, can I now find out all the non-trivial excitations in starting with a trivial product state? And you found that on top of the 2D product state, the only non-trivial 1D circuit is this with Z2 symmetry, say, it's this GHZ state. It's a superposition of a 0 state plus superposition of 1 state. And you found a sequential circuit can do this, starting with a trivial product state, can map it to this long-range entangled defects. So then we ask, okay, can I classify all the low entanglement excitations? And then if you were starting with this trivial ground state, the classification is very simple. The 0-dimensional defects can only be Z2 charge, and the 1-dimensional defect can only be this 1D GHZ state or symmetry breaking state. So in this way, we can classify all the excitations. But what about if we start from an entangled ground state, not this trivial one? And the next, like simplest non-trivial entangled state is this invertible phases, such as SPD phases or Marana chains. And then we found the result is low entanglement excitations in an invertible phases, and those in a product state, they always have one-to-one correspondence. Basically, we find like there's a map that goes in both directions. So, for example, if you can compare in 2D, if you have a Z2 paramagnet, and you can also have a Z2 SPT phases, then the 0D excitations has one-to-one correspondence, and 1D excitations also have one-to-one correspondence. Actually, we claim that we exhaust all the excitations in the SPT phases. And you can find similarly for kinetic chains in P plus IP superconductors. So this result can be get from several ways, but here I want to present a very new way. And we want to use the argument of this symmetry topological order or symmetry TFTs to get that result. Basically, because we found there are some invertible defects that can be created by finite depth local unitaries in the symmetry TFTs. And using that, we can reach that result. So let me show you this argument. There's two steps. First, we're going to compare boundaries of topological orders. So give a topological order with one boundary. We're going to see when we can find some emergent symmetries in the topological order. And that those symmetries are generated by some finite depth quantum circuit. and there are genuine symmetries in the bulk, but they change the boundary condition. And then the second step is that we want to construct an invertible faces using this topological orders with boundaries. And by sandwich this each of these pictures, we'll get first trivial invertible faces and non-trivial invertible faces. And that's our starting point to compare the excitations within. So, okay, let me remind you a bit about topological orders with the boundaries. For example, the most basic example is Topological. It can have two types of boundaries. One is the E anion is condensed. The other is M anion is condensed. And we want to ask what's the relation of these two boundary conditions. And basically you find that there's actually a 2D finite depth circuit, the same circuit that the pump circuit I showed you, because it's the push EM exchange line to the boundary of this finite depth circuit. When you apply this circuit to the whole space, it preserves the bulk to be a Z2 toric, but the boundary type is changed. It's once you apply this finite depth circuit, it's a Z2 circuit. It switch between the M condensed one and the E condensed one. And then we can reach immediate conclusion is that there's no experiments you do only near the boundary that can tell you if you are in the E condensed one or the M condensed one. Because if you want to do any experiments near the, say, one boundary, you apply some unitary operators like k-dimensional support near the boundary. And because there's a finite depth local unitary can maps this operator to another operators, which always have the same dimensional support and also localized on this boundary. So any expectation value, say you compute it here, you'll get exactly the same result here. That means just by doing experiments only near the boundary, there's no way to tell if you're in an E condensed boundary or M condensed boundary. So for that, we say that there's no absolute distinction between these two boundary conditions. If you localize yourself only within one boundary type, you can never know which one you are. Nevertheless, these two are generally two different type of boundary conditions. How we know that? We know that by putting the two boundary conditions simultaneously, and then we can create a domain wall between. And then we can find that this domain wall is always non-trivial. There's no way to trivialize this in the sense that if, say, you create this kind of geometry, this toric with a 4-segment of boundary, and two are E condensed, two are M condensed, then there's non-local operators, a pair of non-local operators that goes along two directions. Basically, there's some operators that generate some that can commute with your ground state. So that means your ground state degeneracy is 2 here. And there be these two degenerate ground state are flipped by non-local operators. That means that there's no local operators you can apply only near this domain walls to change this ground state degeneracy. So this degeneracy is like non-locally, non-local. That means that this domain wall is a non-trivial domain wall. It cannot never be removed by a local unitary.
Can I make a question about the previous slide? So can you just explain why my intuition is wrong? Because I thought that if I have E condensed boundary, like it absorbs E particles in a way, and M condensed boundary absorbs M particles. So if I have both, I can't distinguish the two boundaries?
Because you have like pre-named what is E anion or what is M anions. You say that this anion created by X operator is your M anion, but that's a pre-labeling. Basically, you have a reference in the bulk. You said this is the M anion, and then you can tell. But if you don't know that, if I have, let's say, this some operator that creates, say, E anion here, and then I can use this finite depth circuit to map to another operator that creates this another corresponding anion. And if you just try to measure the expectation value and all those things, you'll get exactly the same results. So by reading your measurements results, you couldn't tell.
This is just stating that there is like EM duality, right?
Right. It's the same thing, but that's the feature. Yeah. So the end result is that there's two boundary conditions. There are, so if in a topological order, there's some invertible line defect, then by sweeping that line defect, you always can get an emergent symmetry of the bulk. And that symmetry is generated by a finite depth quantum circuit. And even though they act trivially in the bulk, it can sometimes change the boundary types. But these two boundary types are only relatively distinguished. You can say that these two boundaries they're related by finite depth quantum circuit. They're twins. So that's the simplest example. Then it also works for higher dimensions. For example, if you have a 3D toric code where the excitation is a flux loop and a point charge that is boson. First of all, you can let the flux condense on the boundary. And there's this canonical M condensed boundary. Then in 3D toric code, there's something called gauged SPT defect. There's a 3D finite depth circuit. Now on the surface of it, it pumps of a gauged SPT, Z2 SPT. So that means there's also a Z2 emergent symmetry in the toric code. When you apply that circuit to this whole system, you will change the boundary type. So just by comparing the two, absolutely, you won't tell that you actually get a different boundary condition. But if you put together, they're absolutely different because you can do this like braiding experiments. So if you're on the surface, you have one is this M condensed boundary. The other is this twisted M condensed boundary you get from applying that finite depth circuit. Then if you have a flux loop, you push it to the boundary. You now can have endpoint. Then if you create two of them, and then let one braid around another in this fashion. In fact, the endpoint of the endpoint when it ends on one of the boundary conditions, if that is bosonic, then the endpoint and on another boundary conditions is always semionic. So when you do this braiding statistics, because there's only one semionic endpoint, you will always get a -1 sign. So that tells you this a 1D domain wall is always trivial. You can not remove it by any 1D finite depth local unitary.
Is there any sense, and can you go back to the picture? This 1D defect that you have on the boundary, it doesn't extend to something in the
It doesn't.
It doesn't. It only is defined on the boundary.
Yeah, you can literally write exact solver models to write out that boundary condition. And the stabilizer you get is you get those surface stabilizers by applying that finite depth local unitary.
Kind of like half of the 3-loop braiding somehow. Usually you do this. There's this 3-loop braiding procedure in the bulk. Here it's like you kind of do the same.
Yeah.
And instead of the base loop, you have this domain wall on the.
It is exactly the 3-loop braiding. So, yeah, if you can somehow create this geometry, let me say, you can gauge this SPT defect, gauge this SPT, then you get twisted Z2 times Z2 gauge theory. And then in that gauge theory, you literally have 3-loop braiding. So what it means that if you somehow this domain wall can make it like dynamical, then it's really recover your 3-loop braiding in that twisted gauge theory. So okay, so we learned how to obtain two different boundary conditions by applying some finite depth circuits once you have invertible defects. Now the second step is to get invertible faces using this symmetry TFT construction or sandwich construction. Maybe many of the audience already know, at least I thought I assumed that, but just a few words to recap. So what we mean is that basically we found that if the bulk is a topological order, then when you consider the boundary, you will find that if you consider all the operators, local operators can write on the boundary that commute with the bulk, and carefully keep track all the states on the boundary, then you find that the boundary forms a system that's only a symmetric sector of this D minus one dimensional system with a global symmetry. And then you can expose that global symmetry by using this sandwich construction. For example, if you have a 2D toric code where one dimension is very narrow, and then this say on the top you put this this boundary condition that E anion is condensed, and then the single Wilson line of E anions becomes local operators in this quasi 1D system. And when you squash this system, it becomes a 1D system with a Z2 global symmetries. So, for example, if now you take the boundary, bottom boundary, sorry, okay. Okay, so what I say here is a picture, and then you can find all the operator correspondence in very exact way. And then we try to use that to get some non-trivial invertible faces. One example you can get is like you can actually also consider fermion condensed boundary of toric once you allow physical fermions. So the emergent fermion can pair with the physical fermion, forms a bound state and condense together. And then you can define the fermion condensed boundary. And this is a exact solvable model to capture that. And then we can consider, like, we put this top boundary to be a fermion condensed boundary. And then if you squash it, because this fermion line become a local operator, you'll get a 1D system with a Z2 fermion parity symmetry. So you get a 1D fermionic system. And now we can do that if we put the top to be fermion condensed one and the bottom to be E anion condensed one. Then you'll find that this whole system becomes a system that the Z2 fermion parity is still preserved. And then if you put the bottom boundary to be M condensed one, you by attaching the EM exchange the invertible defects, you will get another 1D system still with a Z2 symmetry. It's still symmetric. So then what are the 1D phases you get? You only have two options in 1D that have a Z2 fermion parity symmetry. One is the trivial superconductor, the other is a Kitaev chain. And the conclusion is that, yes, you can get two of them, and I know that they must be different. One is the trivial superconductor, the other is a Kitaev chain. But which one is which, you will not know unless you choose some reference, like you secretly pick a reference. So that means through the two sandwich, we can get the trivial superconductor and the Kitaev chain. And now, then we can found that. So if you want to get the symmetric operators in one basis, you in the sandwich picture, you apply some unitary operators near the bottom boundary because that's where the dynamics lives. So whenever you have some symmetric operators near the bottom boundary, you can use that 2D finite depth circuit to get a corresponding operator in this sandwich. And so all the operators here and here near the bottom boundary, they're related by this 2D finite depth circuit. So that way we found that the symmetric operators always have one-to-one correspondence. And the low entanglement excitations are a subset of those symmetric operators. So they also have one-to-one correspondence. So the conclusion is that if you only use Hamiltonians, which are symmetric local, sum of symmetric local operators, or any other symmetric operators, you can never distinguish whether you are in a trivial superconducting phase or a Kitaev chain phase. And then this picture also generalized to higher dimensions. For example, if we take the 3D toric code with the E condensed top boundaries and let the flux to condense on the bottom, when we squash it, we get 2D, sorry. We have a 2D Z2 symmetries. And then you can twist one of the boundary conditions by that surface defect. Then you get another 2D system with Z2 symmetries. And one of them is a trivial symmetric phase. The other is SPT phases. And and you can also find the one-to-one correspondence of their low entanglement excitations. So that's our applications of symmetry TFT and combining with codimension 1 invertible defects. We found that you can generate a lot of different boundary conditions using invertible defects. Now we want to focus on one particular boundary conditions that can be obtained by this way, and found if there's some new things we can learn about it. So the particular example I pick is this Marana chain defect. That's a line defect in 3+1D fermionic toric code. And for that, I want to introduce this topological sectors of topological orders in a sandwich picture, because that's the tool we were going to use to figure out more boundary conditions. This is very familiar in this once the bulk is a 2D topological order. I think it's probably familiar to everyone here. Let me remind you the notation we use here. So in this sandwich picture, the top is some gapped boundary, and the bottom we left it to be unfixed. But the bottom is actually forms a different topological sectors depending on whether there's anion tunneling between the top and bottom. So if you start from some reference bottom boundary state called like vacuum 0, then by tunneling an anion in a vertical way, you get another state. And all these states, they form the eigenstate of your symmetry generators. The symmetry generators are line operators lying parallel to your boundaries. And their eigenstates with eigenvalues specified by this modular S matrix. So tunneling anions in the vertical directions, we get the different topological sectors. They're labeled by eigenvalues of symmetry generators along the horizontal directions. And then using this way, we can record any state on the bottom boundary. We can expand any bottom boundary state in this basis, and with a coefficient. And what is a gap boundary state? Those are the states such that those coefficients are non-negative integers. For example, it can be 0 or 1, and that's basically counts because it's a gap state. So in this low energy effects theory, it only counts how many states in the ground state. And if it's 1, means that this particular anion tunneling state appears once. So that's why these coefficients must be non-negative integers. And the second condition is that these boundary states need to be invariant under the bulk SL2Z modular transformations. You can apply some because this boundary states essentially is states that living on 1+1D space time. Then you can apply this, and if it's a generally purely 1D system, and you can apply this modular space-time transformations on this space-time torus. And this state needs to be invariant under that transformation. And how it's transformed exactly, well, according to the bulk modular matrix. For example, all your familiar E condensed boundary and M condensed boundary, they satisfy the equations. And then what we do is to, in this new work, we generalize this to higher dimensions. We found a way to organize those topological sectors in, for example, in this fermionic toric code example, the symmetry generators are surface operators that generates loops along, say, this XY plane, and the and the fermion-Wilson line operates along the X directions and Y directions. Those are my symmetry operators. Then to get different topological sectors, I need to tunnel some topological excitations from the top to bottom. And there are three distinct ones. One is you tunnel a single fermion. The other is tunnel a flux along the y direction, or you tunnel a flux along the x direction. So you got eight topological sectors in total. And these states are eigenstate of the symmetry operators. And in the literature, this is known as the minimal entropy state, because this is the state you need to extract the topological entanglement entropy. They saturate the topological entanglement entropy comparing to other ground state you can get. And then all the boundary states can be expanded in this basis. And in a similar fashion, the gapped boundaries, they need to satisfy that this coefficient must be non-negative integers. And now this boundary state need to be invariant under the Bock SL3Z modular transformations. So initially we saw this as a bit forbidding task, because how do you get the complete modular matrix for the 3+1D topological orders? Even though SL3Z has only 2 generators, the modular S transformation basically rotate the X to Y, Y to Z, and Z to X, the 120-degree rotation, and also a T matrix, for example, a T matrix in the XY plane. But it's a non-trivial task, got the modular S and T matrix. And then we found in some literature, you can like literally calculate this modular matrix in the so-called worker-1 basis. You can write all this topological order in terms of a worker-1 model, and then that basis, it's straightforward, or not so straightforward, but still it's computable. You can get that modular S and T matrix. And in this case, it will be some 8x8 matrices. And we found that, and we can compute what's the invariant vectors. We found 3 solutions we understand. We actually find 4 solutions, but the 4th solution doesn't make sense, so I'm not reporting it here. The 3 ones that we had nice physical means is this 3. So let me explain what are they. So the first one is kind of like in this MES basis. Basically, the first qubit is whether there's tunnels of fermion. The second qubit, whether there's tunnel of flux. And in terms of the boundary, that means this odd column, like 1, 3, 5, 7, they have total fermion even. And then the 2, 4, and 6, 8, their total fermion is odd, because one fermion is tunneled from the top to the bottom. And the second qubit and the third qubit specify the boundary conditions. If you have a flux that's lying in the y direction that's tunneled to the bottom, that means the fermion satisfy periodic boundary conditions along the x direction. So you change the boundary condition from anti-periodic to periodic. So this 3 qubits basis basically specify the boundary conditions along the x direction, y direction, and total fermion parity. Then you can read off this state. So this states like all the flux tunneling state of tunneling. Once there's a flux tunnel, we found one state in this vector. That means all these 4 states have degenerate ground state. So that means the flux is condensed on this boundary condition. So the first one is a flux condensed boundary. And the second one means that if you tunnel a fermion to the bottom boundary, it costs the same energy as the vacuum. So that means the fermion is condensed on the boundary. So the second vector represents a fermion condensed boundary. And then you can ask, what's the third? What does that represent? In fact, we found it represents a composite loop condensed boundary. So the composite loop is a pi flux bound with Majorana chain. So how do we get that? If you compare this vector with the flux condensed vector, you find that most of the time they're the same. The first 2 qubits are the same. unless you reach the final qubits is changed. If you have both the X flux and Y flux is tunneled, then the total fermion parity change from the even one to the odd one. So only if you tunnel two flux on the along two different directions, your total fermion parity changes. That is that's its consequence of a Majorana chain. So how do we see that? Let's say if I take this composite loop, pi flux bounds with Majorana chain and let it tunnel through, and see how can I get those states here. If I'm like for the first qubit, I'm only tunnel a fermion, they're the same. And if I tunnel this composite loop, if I only tunnel one of them along the Y direction, there's no flux. Majorana chain like they have the same partition function as the trivial chain. So it records in the same row in the vector. However, if I tunnel this composite loop along the Y direction, and then tunnel the second composite loop along the X direction, this second loop was along the X direction. It has periodic boundary conditions along the X direction because there already exists a flux along the Y direction. And then the Majorana chain that has an effect. Majorana chain, once it's the pi flux, it changed the fermion parity from even to odd. That means simultaneously, you need to tunnel a fermion through from the top to the bottom. That's why the fermion parity is changed once the two flux is tunneled. So this vector represents this composite loop condensed boundary.
You mentioned there is a false solution. And it's ill-defined. Can you comment on that?
It has two vacuum. The first component is 2. So it might not be the simple solution. It might be,
So it's not.
yeah. And then we can still use this vector partition function to study gapless boundaries. So in that case, this vector partition function needs to be covariant under this bulk SL 3Z modular transformations. And then the interesting transition is between these two different types of loop condensate. And the theory to describe that should be a single Majorana cone theory. That's based on the intuition of the phase transition from the trivial superconductor to the P plus IP superconductor. And if you and then you can really write the Majorana cone theories depending on the boundary conditions as this vector partition function. And then you find that using this bulk SL 3Z transformations is indeed transformed covariantly. So it confirms that this Majorana cone could be a legitimate critical theory on the boundary of fermionic toric code. So we know that this is a transition between two loop condensates. So we want to see how can we track that? How can we identify this loop condensate behavior with at this critical at this transition point? So basically, we want to how we detect this loop in this single Majorana cone theory, and for that we calculate the zero point energy once we have flux inserted. So basically, this using the sandwich picture. The bottom, you can choose either the loop condensed one or the composite loop condensed one, all at the transition. And the top, we choose this fermion condensed boundary. Then this becomes a quasi 2D system with fermion parity symmetry. And then we fine tune the bottom boundary to this critical point. In this way, we can trying to insert flux along X direction and Y direction, so change the boundary conditions. And so we compare then we compute the 0 point energy. We compare the 0 point energy for the PP sector reference to the APP sector. So that's like you insert a flux along the y direction. So this is the flux energy in the periodic boundary conditions. And you can also do a consider the difference between AP and the PAP sector. That's the flux energy in the with the AP boundary conditions. And then we keep track of this difference. We found that in the gap spaces, so that Marana-Kohn theory, when you adding a mass term, we found that this two difference always falls into this exponential decay. So whenever you have a mass, this different energy difference becomes exponential. Means that these two sectors we saw without the flux inserted, their energy is almost degenerate. And when you tune it to that fixed point, the energy will be exactly the same. That's what the limit where it's labeled by that 1, 0, 1, 0, 1, 0, 1, 0 vector. And then if you tune it to the critical point, we found that this energy difference falls into 1 over L scaling. So previously their energy is almost degenerate. Now there's a single flux. The energy difference is it's almost like a gapless excitation near the transition. And this coefficient is some universal number that depending on the aspect ratio. And this is the energy cost of the single flux. And for the composite loop, the energy cost will always also be the 1 over L at the critical point, because the composite loop is different from the trivial flux by a Majorana chain. So that's only like adding an extra fermion, a single point fermions, once the boundary condition is periodic. And since the single fermion has 1 over L energy cost, so the composite loop also have 1 over L energy cost. And then we can use this energy difference to like distinguish the behaviors in this phase diagram. So in these two different sandwiches, one will get this trivial superconductor, there the P wave superconductor, and only at the critical point, the energy difference become 1 over L. And near, for the two gap states, it's exponential decay. Yes. So with that, I want to conclude. So we found two applications of this sandwich picture plus invertible defects. One is that we found that low entanglement excitations in invertible phases, and those in a trivial phase always have 1-to-1 correspondence. And second is we found that if you always keep track of this kind of descendant defect, such as Majorana chain defect, they can always generate some distinct boundary types. And then there's a lot of open questions we can consider on top of that. I'll just list them here. Thank you.